When adding and subtracting vectors, we need to make sure our vectors are in vector notation with I, j, and k. There are some equations that can be used to go back and forth between vector notation and magnitude and angle vectors, but we'll go over them later. For now, we'll go over adding and subtracting. When adding and subtracting vectors, we need to remember that I, j, and k are separate components, which means that when we add or subtract vectors, we don't combine these terms. You can think of it like x and y. When we do addition with x and y, we don't add them together because they could have different unknown values. In the same way, we don't add I, j, and k because they're in different directions. Now that we know that, let's try adding some vectors. Here we have vector 1, which equals 5i plus 4j minus 7k, and vector 2, which equals 7i minus 8j plus 3k. Now we'll find vector 1 plus vector 2. For addition, the first thing we need to do is combine like terms. So we put the i's here, the j's here, and the k's here. Now we can add each component separately. So 5 plus 7i is equal to 12i, 4 minus 8j is equal to negative 4j, and negative 7 plus 3k is equal to negative 4k. So our answer for v1 plus v2 is 12i minus 4j minus 4k. Now let's try subtraction. Subtraction is almost the same as addition with only one difference, and that's distribution. When we subtract a vector, since we can't combine components, we need to distribute the negative to each component separately. Let's try finding v1 minus v2. Here, what we want to do before combining like terms is to distribute this negative to the I, j, and k components of v2. Now that we've done that, let's try combining like terms and solve. So here we have 5 minus 7i equals negative 2i. 4 plus 8j is equal to 12j. And negative 7 minus 3k is equal to negative 10k. So our answer for v1 minus v2 is negative 2i plus 12j minus 10k. Now that we know how to add and subtract vectors, let's go over how to go from magnitude and angle to vector notation. Sometimes, when a physics problem wants us to add or subtract vectors, they give us the vectors in magnitudes and angles. The good thing is that we have equations to go from magnitude and angle to vector notation. The first equation we'll go over is one that is used a lot in physics courses. This equation says that the component of a vector is equal to the magnitude of the vector times cosine or sine of the vector's angle, theta. This equation can be used to convert magnitude and angle to vector notation for I and j, but not for k. Let's try using these equations to find the component form of a vector. Here we have a vector with a magnitude of 14 and an angle of 150 degrees. Let's try to find the component form of the vector using the equations. To find the I component, we need to use the equation with cosine. So here we have our I component is equal to the magnitude 14 times cosine of theta, which is 150 degrees. If we plug this into a calculator, we get the I component is equal to approximately negative 12.12i. Now, let's look for the J component. Here we have the J component is equal to 14 times sine of 150 degrees, which gives us 7j. Using these equations, we were able to go from magnitude 14 and angle 150 degrees to vector notation with negative 12.12i and 7j. There is one more equation we'll talk about, which lets us use I and j components to find the angle of a vector. The equation says that the angle of a vector is equal to the inverse tangent of the absolute value of the j component divided by the I component. When using this equation, there are two things to remember. First is that even if one of our components is negative, we need to use the positive value because the component is an absolute value. The second thing to remember is that we need to add or subtract the inverse tangent based on where the vector is pointing on the unit circle. If you remember from pre-cal, the unit circle is made up of 4 quadrants, each 90 degrees wide. This inverse tangent equation only works in the first quadrant, from 0 to 90 degrees. In order for it to work in other quadrants, we need to add or subtract the inverse tangent from a certain amount of degrees for each quadrant. For the first quadrant, we can use the equation by itself, like we said earlier, because it works from 0 to 90 degrees. For the second quadrant, we subtract the inverse tangent from 180 degrees. For the third quadrant, we add inverse tangent to 180 degrees. And for the fourth quadrant, we subtract inverse tangent from 360 degrees. Now the question is, how do I know which quadrant the vector is in? Well, we can check by using these rules. If I and j are positive, it's in the first quadrant. If I is negative and j is positive, it's in the second quadrant. If both are negative, it's in the third quadrant. And if I is positive while j is negative, it's in the fourth quadrant. We can use these rules to figure out which quadrant it's in, so we can use the correct equation. Let's try solving for the angle of a vector negative 5i plus 8j. First, we need to use the rules to find the quadrant. I is negative and j is positive, which means it should be in the second quadrant. So we'll use that form of the equation. So here we have 180 degrees minus inverse tangent of positive 8 divided by positive 5. Remember that we make both I and j positive because of the absolute value. Now we solve for the angle. When plugging this into a calculator, make sure it's in degrees and not radians. So our answer for the angle of the vector is about 122 degrees.